So welcome to the this week and a new session in advanced machine learning. So the topic today is essentially to dive into the basics with mathematics of convolutional neural networks. And what you could say is that with convolutional neural networks, if you want to be a little bit, well, perhaps not exaggerate, but what we could say is that what we normally tend to label as the deep learning revolution, this is something which was really spurred by the development of convolutional neural networks. I mean, the basics were developed in the 90s, but it really took off around 2010. And with then the possibility to actually classify, recognize images, etc., etc., etc. This is one of the really success histories of deep learning methods. Now, as a kind of overarching view on it, if you think in terms of the words reducing dimensionality, because if you look at a neural network, if you now have images with, let's say, 200 times 200 pixels, no colors, so just black and white, that means that you would have an input dimension of 40,000. So there would be 40,000 input nodes. Clearly, you would scale down the image, but if you have millions of such images, this becomes a huge problem to deal with, especially if you're using standard neural networks, because in that case, what you're doing is just a set of matrix vector operations, and you typically do that with dense matrices. And that means that the dimensionality quickly becomes too large. So you can think of CNNs as a way to extract the most important properties of an image, and then use that in the development of an algorithm, which allows you to tell whether this is a house or not. So if you think of a house, what you're doing then is that you are developing a filter, and that is where the mathematical process of convolution kicks in. So you develop a filter where you take care of the important properties of a house. So if you think of a house, obviously, if you want to classify it, you have doors, windows, eventually a balcony, corners, and the roof. So these are the most important features which you would like to keep. Obviously, the color of the house, unless you've been doing a bad painting job, is assumed to be uniform over the house. So that means that you will not take, let's say, keep information about just the parts of the wall where there's nothing else than just the color of the house. So the CNNs, the way you have to think of it, because it's defined, it's called convolutional neural networks, because it's simply using the mathematical process of convolution. And what happens then is that you're trying to filter out properties which are not relevant. So one thing with many of these CNN codes which exist with dataset, pre-trained datasets, is that they have often been tuned to specific sets of images. Suppose you want to recognize cats or dogs and so on. You can have special filters which are trained on that. And you can have special filters which are trained on houses or buildings or cars or whatever. So that means that when you're applying CNNs to your specific field and your specific data set, you may actually have to think of making specific filters. So in our case here, the way we are going to deal with them is that we are going to use the different filters as a type of parameter. So you would set a filter, and that becomes a so-called hyperparameter, which we then use throughout the calculation. And then you change it, and then you see if you get better results or worse results. So this kind of numerical experimentation is something which is part of the CNN structure. So I'm going to go through some of the basics and then look at the mathematics of convolution and how some of these parameters, so-called hyperparameters, why we use them and why they are useful. Now, one thing which I wanted to say before we continue, if you now go back to the GitHub address, so what you will find, because we've been discussing back and forth what kind of projects we should deal with. So if you go into proposals for 26, several of you have actually made proposals. So during the lab sessions today, there is still a possibility to present projects. But for those of you who are undecided, take a look at those. These are suggestions by you. And if somebody finds that topic interesting, you could join other people. So please feel free to do that. And then secondly, if you go into the 2026 folder, you will find some different variants which I'm proposing. So this is very much based on what many of you have proposed or are thinking of. So feel also free to view these as suggestions. That means that you can change them by placing in your data sets. You can add things which you find more interesting. So these are just loose schemes. So there is obviously one on CNNs, which we will start discussing today. And some of you who have taken Physics SDK 4155, you have seen a lot of this material before. But I thought of going through this anyway, so that you have a better feeling of what CNNs are. There is one on generative methods, which can be seen as a semester-long project, where you start with CNNs, but then you can use generative methods like variational autoencoders, Boltzmann machines, diffusion models, and apply these to the same data, and then make a critical analysis of generative and discriminative methods. Then there is one which I called mathematics. And this is something which could be interesting for those of you who would like to explore the mathematics of deep learning methods. So many of you, especially if you've taken the course Phys SDK 4155, you have written a code for a neural network. And some of you may be interested in exploring the mathematics in more depth. So this is another possibility, and that's this project we call MAP. There are then two on ordinary differential equations and PDEs, which also deal with using physics-informed neural networks, but you can dive into either a partial differential equation, like we discussed last week, or you can dive into an ordinary differential equation, like a, let's say, coupled pendulums, if this is something which is of interest. And finally, there is something which I just call Project 1, which is a little bit more generic and just sketches different paths. But then the other ones are slightly more specific into a certain direction. So after the lecture, we're going to just, I'm going to say a little bit about these, and you can take a look at them, and keep in mind that you can modify these as you want. These are just suggestions. So we are a very heterogeneous group in this class, which means that people have many different interests, and we are in a way trying to find a common denominator, which will be the lectures and the topic we discuss, but then many of you want to go along your own paths. Okay? Any questions about this? So what I want to do now is to say something about the convolutional neural networks and the basic mathematics and the operations which we're going to deal with. So I'm going to use a mix of the whiteboard and the Jupyter notebook, which you all have access to. So there are some reading recommendations here, and clearly the book of Goodfellow et al. Gives a pretty good introduction. There are some nice videos if you want to look at them. And then I just wanted quickly to remind you of some of these books on the mathematics. So if somebody is interested in more studying the mathematics of deep learning, these textbooks can actually be interesting to link to such a path for the projects. So if you do that, that would typically be a 1 semester long project. There is also the possibility, and if you look into the slides for this week, there's an example on how you can write your own CNN code. So every semester, there's always been a group of people who want to write their own CNN code from scratch. So this is also another possibility. But that is something which I normally recommend to think of as a 1 semester long project. So I hope I'm not giving you guys too many options, because at a certain point you would like to nail it down. This is what I want to do. Okay, so this is mainly It's also used for regression problems. People have used CNNs to solve differential equations, but it has mainly been used to deal with imaging. So if you take a course on imaging, it's very unlikely that you will not meet convolutional neural networks. So what I wanted to say a little bit about is the main structure. So what I'm doing now is going to switch over to the whiteboard, and I wanted to say something about the basic structure of a CNN. And when doing this, I'm also going to say something about the type of parameters which you're going to meet. So a typical convolutional neural network has obviously the input layer. So let's just look at, take an overarching view on CNNs. So it typically contains the input layer. So let's just write that. So this would be the first layer where you just input your variables. So these are the x's. So I'm just setting up this in a simplified way. Now, your images can be pretty large. As I said, if you have an image with 200 times 200 pixels, which is not uncommon, that MNIST dataset has images of at most 28 times 28. So that means that many of these handwritten numbers are pretty blurred. But if you have a high resolution image, it's typically a 200 times a 200. So the input layer is something you want to reduce, and that is where you have this convolution stage. So let me just set that up, and we are going to put that we are going to label that in terms of conv stage. So that's the convolution stage, and that contains typically 3 main elements. So one box which we put in here is the mathematical convolution itself. So just using the shorthand convolution. And here we are going to apply a filter on the incoming data set. So that filter which you have is going to reduce the dimensionality of your image. And it will pick parts of the image, only parts of the image. And then it can make many replicas of the image. So suppose you have a 200 times 200 image, then you scale down parts of the image to, let's say, 50 times 50 pixels. But then you make 10 replicas. So then you have 50 times 50 times 10. If you have colors, there are typically 3 color channels, R, B, G. So that gives you an additional 3 in dimensionality to keep track of. So a typical color image has 200 times 200 times 3, 200 times 200 pixels. So you can think of these as X and Y coordinates. And then you have the color channels. And then you can reduce this. So you would typically, in the filter, you would take parts of the image, and then you will make replicas of this image in, say, something like 10 smaller images. And then when you've done that, so that's the filter itself, and we're going to look at what it means actually. Then there is something which is now called a detector stage, which sounds very strange, but you often have an activation function here. So, and the typical activation function is a ReLU. Then there is another stage here where you reduce the dimensionality further, and that's called pooling. I'm trying to squeeze in all these names here. Now, pooling is so suppose you have a fraction of your image, which now is composed of 10 times 10 pixels. Then from this image, you pick the largest value, and you only keep that one. So that's a way to downscale the image further. So with the convolution stage, you can make replicas, but these replicas are often smaller parts of the image. And then you reduce the dimensionality And by the convolution stage, you are now ready either to plug this into a standard neural network because you have reduced dimensionality and you can do the training there. Alternatively, you can do more convolutions. So many of these deep layers, deep convolution neural networks, they have many such convolution stages. And the type of filters you apply depends very much on the type of problem you have. So we are in this course, we're simply going to use the predefined one, which you have in libraries like PyTorch and TensorFlow. But for many of you in your own research, it may actually be more of interest to tailor this to a filter to a specific problem. So we have Fourier expansions, which are very much used in the filtering. So think of now this as you can have many, so I'm just going to write in here, we can have many convolution stages. And one of the things I wanted to say here while we are setting this up is that in this part, we have the parameters of the filter, which are trained by backpropagation. So these are filter parameters, and we are going to see quickly now how these filter parameters appear. Filter parameters. And these are trained by backpropagation. Backprop. Now, the ReLU stage, you can replace the ReLU activation function with other functions. That is a stage where you have fixed the parameters of the activation function. So that means that there are no parameters to be trained. So remember that in the training, you update the weights and the biases. Now, in the ReLU stage, or detector stage as it's called, where you further can reduce the dimensionality of the problem, you have only hyperparameters which define the activation functions. So no parameters to train, but only parameters which are fixed before you start the calculation. So let's now mark that one so no parameters to train. So we have only the hyperparameters. The pooling stage is also set. So the standard approach is to use either something which is called max pooling, where you take the largest value from a fraction of the image, or you take the average of the values in that fraction. So that's called max pooling or average pooling. And we are coming back to those. In that case, which one of these methods you use is defined before you run the calculation. So keep in mind that when you're setting these calculations up, you have an architecture. The architecture is part of your model, but some of the parameters are fixed before you do the training. So the weights and the biases are trained by backpropagation, gradient descent, etc. But then you have other parameters which are fixed, which means that you end up doing many numerical runs in order to test different hyperparameters. So in this specific case here for the pooling stage, this is also fixed from the beginning. So we write this as a fixed part of the architecture of the network. And here we also have no params. It's the same situation as we have previously. Then when we've done with the convolution stage, you can have many such stages, but then the next stage is normally the neural network, because now you have scaled down the images. You made many replicas of the image, which are normally smaller ones, and then you feed this into a standard neural network. Now, this standard neural network does exactly what we've been discussing earlier. It has all the backpropagation, the training of the weights and the biases, and then it spits an output, which then feeds into your cost function, loss function, and then you compare with the target values, and then this goes back and forth. So the depth of the network can actually be pretty deep with many convolutional stages and also many layers of a hidden neural network. So I have to go to the next page if that is okay. So that means that the next stage is just a standard feed forward, NN. And in that case, what we have is activation functions, which are set by the architecture, which you have chosen. And here you train weights and biases. Plus biases. The network itself, the architecture for the feed forward part is set by you. So that would be a part of the model and architecture as well. So this feeds in here. And what you will often see is also is that the data which you have is now flattened. So this is also called a flattening stage. So it simply means that you transform everything into a long vector. And that is fed into your standard feed-forward neural network. So you see that the feed-forward neural network, when you have written a code for that, this is a basic building block in essentially all the methods we are going to deal with. And then what you end up with is your cost function. So you have some cost function which depends on the parameters theta you want to optimize. And this feeds in, so you produce an output y tilde, and you compare that one with the target values. Okay, so that's basically how we set up a convolutional neural network. And clearly the depth of the network depends on you and how much CPU cycles and GPU cycles you want to spend. And that clearly sets a limit to how deep and how long you want to train the network. Okay, any questions? So what I wanted to say a little bit now, if you don't have any questions, I wanted to say a little bit about the parameters which pop up when we are setting up the convolution stage. Because we have parameters like padding, stride, which sounds like strange words, but these are linked with the process of the convolution itself. So let's look at a very simple case. So you have an input matrix, which is a 3x3 matrix. And then you're going to scale it down by a filter, which is a 2x2 filter. So let's look at how we set up the process of convolution. And that will also introduce parameters like stride and also what we call padding. So let's just look at this very simple example to give you a feel of how we define parameters for the architecture and how we actually set up the process of convolution. So suppose now that we have a simple input, which we now set up as a matrix. So this is a 3x3 matrix. So 3x3. And we are now setting up the variables. So we just call them x00, x01, x02, and then we have x10, x11, and x12, and then we have x20, x21, and x22. So this is now our data. So this is often typically the way you would set up your data as a matrix. You would flatten it often, but typically this could be your image, right? So you have 3x3 pixels. What could be something else? Then what we are going to do now is to apply a filter to this. So we are going to define a filter which is defined as W00. So it's a 2x2 filter. I'm going to label this as a matrix X, and this is a matrix W. So the filter is something I will label with that one. And this is now a 2x2 filter. And now I'm setting up, these are parameters which I need to train. So the process of convolution, which I'm coming back to the mathematical expression, what I'm going to do now is simply to set up the final result, which is going to be a 2x2 matrix. So we have reduced the original dimension, which is a 3x3, by a 2x2 matrix via a 2x2 filter. So what happens then is that we are going to multiply the way we do the process here. We start here, and now we take this value and multiply with that one. We take this value and multiply with this. this value and multiply with that, and finally this one with that one. That is the new value which we get when we apply the mathematical process of convolution. So we get an omega 0, 0 plus an x, and then we have the x 0, 1 times w 0, 1 plus, and then I have x 1, 0 times w 1, 0 plus x 1, 1 times w 1, 1. So I haven't set up the equations for convolution, but I'm just going to set down basically what the convolution looks like. And then we go back to the mathematics, the mathematical expressions, either for a discrete convolution or for a continuous convolution. But essentially, this is what we end up doing. We are now taking care of some of the values, as you can see. And here we started with this block, and that is multiplied with the dimension of the filter. So we have a 2 by 2 block from the data. Now what we do next is that we now move to this block. So that block of the matrix. And then we perform the same operations on the filter. So that means that what we get then is a new value here where we have x 0, 1 multiplied with w 0, 0 plus x 0, 2 multiplied with w 0, 1. And then we have x 1, 1 times w 1, 0 plus x 1, 2 multiplied with w 1, 1. So what we have done now in this operation is that we have moved one step to the right. And you see now that when you position yourself here, there is nothing after that. This is a variable which, when you do the convolution, you can define, and it's called stride. So, and the stride here is normally labeled by S, and in this case, it's stride 1. So that means that we have this subblock 2 by 2. We identify 2 by 2 block because that's matched with the filter. And then we move one step to the right here, and then we have a new subblock. But after that, if we try to start here, there is no block here. So for this specific case, we can only do a stride equal to 1. So this becomes a parameter in the setup of the filter. Because you could think of, if you have now a 4 by 4 matrix down here, you could now think that you do this block first, and then you just do that block. That would be a stride of 2. So when you do the reduction, it's you who defines how much information you keep with you. So stride is a way to, is a parameter which you need to fix. So stride is a hyperparameter in the setup of the convolution itself. Now, if we now proceed, you see that we made one step here to the right, but now we can go down one step. So that means that we have this block, which you see here, which then is matched with a 2 by 2 filter. Yeah? Yeah. Yeah, exactly. So this becomes a parameter. So, and the thing which is important now is to see how much information you carry with you. So let me just go through this one, and then we are going to look at how some information is present in many of the boxes you see here, and how some information is not present. So let's take a look at the next operation here, which would then give us x1, 0 times w0, 0 plus x1, 1 times w0, 1. And then we have plus, and then we have, so it's all pluses here. So we have x2, 0 times w1, 0 plus x2, 1 times w1, 1. And then we take the final one, which is actually this one. And that final one gives us now x1, 1 times w0, 0 plus x1, 2 times w0, 1 plus, and then we have x2, 1 times w1, 0. And finally, we have x2, 2 times w1, 1. Now, there's one thing I want you to notice here. So if you look at the information which we have now included, you see now that the corners which we have, like this X00. That appears only in one of these slots. X11, on the other hand, is here. That information is here. It's also here, and it's also here. So you carry with you that information in the downscaled matrix due to the filter. But the corners, as you can see with X00, X00 appears only here. If you take X02, which is another corner, this one, you will see that that one appears only here. So let's just mark these ones. So we have X00, X02, X02, and then you also have X22, which is one of the corners, which also appears only in one of the boxes. So depending on how you want to carry information with you, you can then introduce a new so-called hyperparameter. And that hyperparameter is called padding. So padding means that you can put a layer outside here with just zeros. Then what you will have then, if you have this layer outside here with just zeros, is that then your X00 would just be zero, it will be there. But your X00 would then appear in all the boxes you're looking at. So padding is a parameter which is often added in order to have as much of the information you have here in all the possible boxes. So when you look at this, what we would typically do then is to add a new parameter. So you have stride, and then you have a new hyperparameter. These parameters are fixed before you run the calculation. So which is called padding. And normally this is called P. And in the example which we had here, padding was equal to 0. We had no padding. So if you now think of the filter which we put up here, it's also common to bring in a bias, and you see that you have 4 parameters which need to be trained in the filter. So these are trainable parameters of the filter. So in this specific case, we have parameters to train, parameters in the filter. There's a lot of background noise today, so I'm sorry for that. I hope, can you hear well in the back? I mean, there's no problem. So the parameters to train are the 4 weights which we have. So W00, W01, W10, and W11. And then you typically add a bias parameter. So in total here, you would have 5 parameters if you're using this filter to train by back propagation. So you run through, you would typically have a feed forward stage. You run through the convolutional filter. Then you run through the neural network at the end, and then you receive an output. You compare that with the target value, and then you propagate back. You update the neural network parameters, and then you update the convolution parameters. Then, if you now think of the parameters you need, if you now look at n, let's define that as the dimension of x. I'm assuming that x is an n times n matrix. You can change that if you want to. And then if we look at f, that is the dimension of the filter. We're also assuming that the filter is quadratic. So that is an f times f filter. And if we then are going to look at the type of the dimensionality which we get, so dimensionality of output, it's actually pretty easy to see that that dimensionality, which I'm going to call N2, the final one, in this case, is given by N. And now we put N1 here. So let's just say N, that this is N1. And then this is the first filter. You can have many filters. You would have N1 minus F1. And this is divided by the stride S plus 1. So if you add padding, then you will have that N2 is going to be equal to N1 minus F plus 2 times the padding. It's actually pretty easy to see that this is the case, plus 1. So if you look at our case, which we have here, then we have 0 padding. We had stride equal to 1. And then we had N1 equal to 3. And F1 equal to 2 then. So if we put that in, then we see easily that N2 is equal to 2 here. So a typical other example, if we now just play around a little bit with this. So let's also mark that P and S, these and also F, these are parameters which are set by the architecture. So these are not trainable parameters. These are parameters which are not trainable. Not to be updated. So many people get a little bit disappointed when they start looking at these deep learning methods because there's such a wealth of parameters. And then you ask yourself, I mean, which one should I choose? So the way you choose this is actually you trying different parameters and running as many as possible numerical experiments as you can. And you have to view everything you do with deep learning as a numerical experiment. So we could take a second example. So we could now have a N1 case where we have a filter with N1 with 32. And we could think of the image as being an image which has colors. So that means that we would do a 32 times 32 pixels times 3 color channels. Then we could apply 10 5x5 filters. So what it means then is that we are going to take parts of the picture, we're going to scale it down, and we're going to make replicas, which we are going to use in the training. So you could now think of taking 10 filters, and each filter is a 5x5. So that means that you're going to have, for each filter, you're going to have 25 parameters, plus a bias, which you need to train, 26 parameters per filter. And you have 10 filters, and that means that you have 260 parameters in total to train in the convolutional stage. So if you then apply this and you set the stride equal to 1 and padding equal to 0, then what you will end up with when you reduce this dimensionality is 32 minus 5 divided by 1 plus 1. That is your new dimension, which is N2, which is equal to 28. So you're doing 28 times 28 times 10 replicas of the image which you have. And then if you include the color channel, then you would have to add a factor, multiply with a factor of 3. So with color, then your filter will now contain the following number of parameters. So that will be 5 times 5 times 3 plus 1 bias. So that is 76. That's for every filter, you have 76 parameters to be trained because you have 3 color channels. So that means in total, what you will end up with then, in total, since you have now 10 images, you will have 776 times 10, which is 760 parameters to train. Now, this convolution stage is something which you can repeat many, many times. So you're not limited to just do one convolution. So in the examples you will see, I'm going to set up deeper convolutional layers, or you can just stay with one layer. So typically when you begin the calculation, you would just stay with one convolution layer. That's a very typical starting case. when you start with convolution. So we can do a further example. And in that case, we can have a 3x3 filter. And we have an image which is 32 times 32 times 3. That is the original image. And again, you put stride equal to 1 and the padding equal to 0. And what you would have then would be 32 minus 3 divided by 1 plus 1. So your dimensionality then is actually 30. But then you have to multiply with the color channel. So you have 30 times 30 times 3. So each image has then a filter with 3 times 3 times 3 plus 1. So each image or each filter. So this is your new dimensionality of the image. So each filter has then 3 times 3. But then you have another 3 here because you have the color channels plus 1. So that means that in total then you have again 28 weights plus 1 bias. So it's 27 weights and plus 1 bias. So these would be the typical parameters which you would need to train them. So when you now look at the setup of the convolutional stage, so we have the following hyperparameters. So there's a parameter which you call K, which is the number of filters. We have F, which is their spatial extent, the filter spatial extent. So if it's a 3x3 filter, then F is equal to 3. We have the parameters S, which is stride. And then finally, we have the padding parameter, which is the amount of padding. So this produces a new image with a given dimension. You can make replicas of this and then continue like this with more convolutional stage. Or when you're happy with this filter, which you have set up here, then you would feed that one into a convolutional neural network. No, not a convolutional, a standard feed-forward neural network. That's the basic stages here. So after the break, we are going to look more at the mathematical process of convolution and what it is going to mean for us. So typical parameters, if we just summarize now a little bit, is to have F equal to 3, S equal to 1, and then a padding equal to 1 here. That's a typical parameter. We have F equal to 5, another very typical parameter, S equal to 1, and then you can have padding equals 0, 1, 2. You have a F equal to 5. So these are typical setups which you will see in the literature, with stride equal to 2, and P 0, 1, 2, etc. And also other types of parameters. But 3 and 5 are the typical dimensionalities which you will encounter in many, many applications of convolutional neural networks. But keep in mind now that these are parameters which you would set up before you start performing the calculations. The training itself, like in a feed-forward neural network, is only something you apply to the weights and the biases. And then if you change the activation functions, the stride, the padding, etc., that becomes a new experiment. And then you would go back and forth like this till you reach a result which you are satisfied with. And that's the basic essence of what we are going to do now. So after the break, we are going to look more at the mathematics itself of convolution and what it means. And the example which I'm going to show you is an example where this padding stuff comes up naturally. And you can see then why you introduce padding in many, many instances. Okay, so should we take a small break, everybody? Yeah. So, yeah.
What's the use of multiple
Oh, the use of multiple filters. So having one thing is that are you thinking of multiple filters connected with you making replicas of the images? I'm going to show you now pretty soon here, so you can see the kind of thing you can do actually, and you will see from the images here. So just wait some few moments, and then we are going to get there. I wanted to repeat some of the things, and then we are going to look at the mathematics of convolution itself in more detail, and how that is implemented in a convolutional neural network. So the typical setup is that you have this input layer where you have an image. It could be a 32 times 32 times 3, and typically the image has a width and a height. There is a convolutional layer where you can output the output of neurons that are connected to local regions in the input. So a specific filter will be connected to some regions of the input, and it's you who decides which regions. And then by making this replica, you can actually have replicas which act on different regions of the input. So coming back to that question about how many filters and how many replicas you make, is that each filter could just act on a region of the image. So if you have a big picture, you can then scale it down to 10 images, which then have information from different parts of the image. Then we have the ReLU layer, and this is a layer where you have no parameters which are trained. And the ReLU layer is just a layer where you can use a max output here, thresholding at 0. This is pretty common, but you can use other ones. You can have other types of activation functions, but the ReLU is the one which is mostly used. And then there is a pooling layer, which is actually a downsampling operation along the spatial dimension. And that can reduce the dimensionality. So in this case, you can have, if you have 12 filters, you can make just copies of the image. So you have more training data, or you can downsize the image if you have a smaller filter. So if you have a filter which is the same size, then clearly you're not doing any downscaling. And then there is a fully connected layer where you then input the image, and then you perform the training. And that's a typical feed-forward neural network. So what you could say is that the CNNs transform the original image layer by layer, from the original pixel values to the final class scores. Some layers of the convolutional neural network contain parameters, and some do not. So the ReLU part does not contain parameters to be trained. It has only hyperparameters. The max pooling has only hyperparameters, etc., etc. So some of the parameters are being trained and some are fixed. So a CNN is the simplest case. In the simplest case, there's a list of layers that transform an image volume into an output volume. There are a few distinct types of layers. You have convolutional, this feed-forward part, the ReLU pool. These are the more standard ones. And here is a typical one where you, which is a picture which I took from this book of Rashka, which you have access to. And in that case, you have an image which is 28 times 28. You have a convolutional layer, which is 5 times 5 times 32, which then gives you, so you're making 32 images. And then you have a pooling layer, and then you reduce the dimensionality. You have a new convolutional layer, and then it continues like this till you have downscaled everything. You have 64 images, which have a dimension 7 times 7. And this is flattened and fed into a feed-forward neural network. And then the output, if this is an output with 10 classes, that is a typical case which you have if you use the MNIST data. So the MNIST data starts with 28 times 28. And then you are outputting numbers from 0 to 9, so 10 numbers, so that it means that you have 10 output nodes. So this could be a typical setup, which we now are going to see how you can encode that in using TensorFlow or using PyTorch. And we're going to look at that a little bit later. So the key idea, if you compare with a standard neural network, which is defined by affine operations with dense matrices and dense vectors, the kind of key idea is, for say imaging, is that in images, neighbor pixels tend to be related. So you connect only neighboring neurons in the input instead of connecting all with the first hidden layer. The problem is that finding the right filter is an art by itself. And that is where you have to bake in the knowledge about your own field and discipline and what the images stand for and what kind of image you want to recognize. So making the filter is an art by itself, and there's a lot of research there. So we will not cover that in much depth in this course at all. Yeah, this is just a kind of digression which I have here. Are you familiar with the singular value decomposition? So singular value decomposition is my favorite algorithm in linear algebra. And even if the matrix is singular, you can always singular value decompose a matrix in terms of a matrix which is orthogonal, multiplied with a diagonal matrix which contains the singular values, multiplied with another orthogonal matrix. So the singular value decomposition is a theorem which simply states that you can always decompose a matrix, always, even if it's singular. And that is an amazing statement itself. Now, a singular matrix, suppose now you have a 100 by 100 matrix. When you decompose it, you get 2 orthogonal matrices, which you then can use to downsize an image. So the singular value decomposition algorithm was the kind of standard way of doing image compression. So you would perform a singular value decomposition on the image. You would downscale it. So if it's a 100 by 100 image, suppose you only keep the 5 eigenvectors with the largest singular values, and you could use these 5 eigenvectors to construct an image. And then you would then have to take care of the transformation coefficients from the full matrix and the downscaled matrix. And when you had those transformation coefficients, you could then reconstruct the full image. So the example which you will find here is only meant as an illustration. And it's an example on how you do this, use the singular value decomposition. So you get a matrix, orthogonal matrix U, an orthogonal matrix V, and a matrix S, which contains the singular values. So this is the original image which I have. And then I'm actually compressing it down to a 5 by 5, 10 by 10, 20 by 20, 100 by 100, and up to 500 times 500. So what I'm doing here is simply just to compress the image. I'm not going into these details. And the image which I have is actually this one. This is actually one of my favorite places in the world. It's a fantastic city in Italy. It's called Volterra. And it was built by the Etruscans. Actually, it has a dated history of more than 4,000 years. And this is actually the medieval part of the city. And this is the image which I'm compressing down. And when you, let me see, why isn't this showing properly here? Okay. Yeah, okay, that's why I was just looking at the very end. Sorry. This is the original image. And now I keep only the 5 eigenvectors with the largest singular values. And you can see now the image is pretty blurred, but you still see that this looks like a house. And then you can increase it. You have 10, it's getting better, 20, even better. And then with 100 of the, because the matrix, the original image is 100, 800 times 1200. And you can now see the, when you keep only 100, it's still getting, it's getting pretty good actually. So this was, yeah.
You not also need to store the U and the V orthogonality?
Yeah, you have to store them.
So wouldn't the majority of memory be used to save those matrices because they're non-sparse?
Yeah.
As opposed to sparse.
Exactly.
So why are you reducing the number of eigenvectors as opposed to just reducing the number of elements in UNV.
No, because you can downsize the image and you can use that one as a way to represent the image, and you only present that one. But then you need to be able to reconstruct it later.
Yeah, but so the whole image can be represented as U times Y, diagonal matrix times Y. And then you're reducing the amount of data you'd save by just cutting out some eigenvalues from the diagonal matrix.
Right.
But why aren't you cutting out any values from U and V? From U and V.
Well, these are the ones which you keep actually. Because if you now have a symmetric matrix, then the two matrices U and V, you have to keep them actually when you do the decompression. If I understand correctly your question here.
Yes, but if you're keeping U and V, how much space are you really saving by cutting out values from the pipeline?
So this depends very much on the type of application. If you're happy with, let's say, this resolution here, then you would just keep that one, and then you could forget about what you had. So if this is sufficient for you to recognize whether this is a house or the place itself, then this is the information you would keep. So you have compressed it. But clearly, if you want to reconstruct, if your task is to reconstruct the whole image, then you don't save anything. But if your task is to have a compressed image and you are happy with that, so suppose now that 100, this k equal 100 is okay, then this is what you would keep.
I think my question is more so geared towards if you're saving U and the diagonal matrix and V, and then you're cutting out elements of the diagonal matrix to save space. Why can you not cut out elements of U and V? Surely those are the diagonal matrix elements are just as
Why you cannot?
Why can you not remove elements from U and V to get space?
In principle, this is, I mean, you're only keeping the vectors from U and V. So you are represented by the orthogonal vectors, and you only keep those vectors which correspond to the largest singular values. So this is your downscaled information. So your matrix, if you have a matrix U, which is 1,000 times 1,000, then you can keep only the 100 eigen or vectors of that matrix, because it's an orthogonal matrix. So every column is an orthogonal, represents an orthogonal vector. And then every column, then you can then say that corresponds to a singular value, and you keep only the largest singular values. So we're actually coming back to the singular value decomposition when we are going to discuss autoencoders. Then we are going to look more at the mathematics, and we're actually going to bring up this example back again. Because so here what you're doing is that if this is the type of information you're happy with, you would then only keep a certain amount of the orthogonal vectors, and then simply leave out the other ones. And that's what you use then to represent the image. Yeah. I just have to take off this headset because else I don't hear properly here. Yes. Yeah. Yeah.
So what you're feeding, what is not what you're.
So what you're feeding?
What you're feeding into the network.
Yes.
Like the not the single and then afterwards when you get the output then you goes as the like less long again. Or what you
So what I'm showing here is just a standalone case without the convolution neural networks. So I'm using the mathematics of the singular value decomposition, which then allows me to decompose the information in terms of two orthogonal matrices. And then I keep those because the matrices are orthogonal. And that means that the vectors, which are every column of the matrix, they are orthogonal, they form an orthogonal basis. And they correspond to some singular values. And you keep the largest ones, which also corresponds to the case with the largest variance. So we are coming back to all these mathematics when we discuss autoencoders. But the thing is that, as you say here, you can actually use what you do here to downscale the image before you use a CNN. Or I can downscale this image, and if I say this is a pretty good representation of the image, I could then feed that one into a neural network. So when we are going to discuss autoencoders, the philosophy of that is pretty similar to what we are saying now. And there is a method which many of you may have heard of, which is called principal component analysis. And that's essentially this. So you downsize an image or an object by keeping the information from the singular value decomposition, which then corresponds to the largest singular values, which then means that you keep track of the largest variance in the correlation matrix. We are coming back to these technicalities. But this is a way by which you can downsize the images you have and then feed it into a neural network or convolutional neural network. But a convolutional neural network is actually meant to do this kind of job for you by starting with a full image. Now, the reason why I brought this up is I just wanted to show you what was done typically till the end of the 90s in the last millennium. And that was a pretty common technique to use a singular value decomposition. So it's you at the end who has to define what is the quality you want to keep. So I should have brought this up a little bit later when we discuss autoencoders, because then you will also have seen the principal component analysis. But it was meant as a digression. So let's scroll down a little bit now, and I'm going to continue using the Jupyter notebook a little bit. So the mathematics of convolution, if you think of this in terms of continuous variables, is essentially given by this equation which you see here. So this is actually convolution. And you could think of this as you making some observations. Suppose this X here is you observing the position of an object as a function of time. And in the beginning, the positions may not be properly measured. And then when you multiply with this W, you're filtering out some values which you don't want to have. So this is one way of reading this expression, but this is essentially what you do with the mathematics of convolution. Okay? Is this example okay? So you can think of this just being measurements of a position as a function of time, and in the beginning you're not doing too well, and you don't like your measurements, and you want to filter them away. Or maybe there's a lot of noise which you want to filter out. So convolution, for those of you, is anyone here taking a course in imaging, classical imaging? So Fourier analysis and all this stuff here, this is something which enters often that type of mathematics in, and then the filtering becomes is a very important. So this integral is actually written out in terms of this X times W, and this is the definition of a mathematical convolution is defined if you have a one-dimensional example like this. If you do a discretized version, this is what it looks like. So what I'm going to show you now is an example which you may find very boring, but at the same time, I use it because I can introduce the concept of padding, also stride, and at the same time, it shows you how we do mathematically the convolution stage in a neural network. Because the way you want to do the operations is to use linear algebra, and that means normally matrix vector multiplications and matrix multiplications. So the basic idea is that we want to filter out some information. So if you keep that as a kind of overarching information, and then clearly the way you design this filter W, that is an art by itself. So the kind of example I wanted to deal a little bit with is actually that of polynomial multiplication. So what I'm having, and you know very well that if you simply write this polynomial times this polynomial, you can actually have a very inefficient algorithm. So everything I'm going to say now is something which will link with convolution, but is also linked with us setting up an efficient algorithm for calculating a polynomial multiplication. So if you look at this expression here, you obviously, I guess nobody disagrees that you should get a polynomial of degree 5. And then what we know then is that this polynomial is going to look like that. I'm going to abuse a little bit with the Jupyter notebook here, because the example is hopefully you can also work it out yourself. So what you can see then when you perform this multiplication is that you can set up these parameters in terms of the coefficients of the two polynomials, the second order and the third order polynomial. Now, one thing, if you go back to the equation you have up here, this one, this is a brute force implementation, and you could think of this x as the high order polynomial, s, and the w as the low order polynomial. So essentially what we are doing now is to use this formula here to perform the polynomial multiplication. So when you look at that, we see that you have for alpha I lives only between 0, 1, and 2, and beta I between 1, 2, and 3. You could now just go ahead and just write this in a brute force way, where you sum from minus infinity to plus infinity. But then you know that there are only some few values which are non-zero. But your mathematical expression here for these parameters, and this is typically the way you do polynomial multiplications, is actually a convolution. It's the same mathematically as the convolution process. So you can actually rewrite these coefficients in terms of this expression here. So when we are dealing with images, what we normally end up with is actually operations of this type here. And you will see that a little bit later when we now are going to replace this one-dimensional quantity in terms of a matrix, an input matrix, which is then weighted by a filter. Okay, so you can rewrite it as a double sum if you want, but this is the expression which we will look at. Now, if you now look at these expressions, you see that you have many redundant operations because you have many zeros here. So it's pretty stupid of us to just run it like that. So we would like to nail this down to just the essential quantities. I mean, those which are non-zero. And then we want to make it efficient from a computational point of view. So let's look at these steps here. So with in this case, with m equal to 3, the maximum length for the vector, which is the maximum length for the vector alpha, because you have the 0, 1, and 2. So let me just go back. So the vector alpha has a length 3. You have only 3 components. And the vector beta has 4 components and length 4. I hope you don't get offended if I repeat some of these things. You could actually rewrite this in terms of a matrix. So, and this is essentially the way you would encode the information when you do the filtering. So you could think of rewriting everything like this matrix. So this matrix has a name. It's called a tuplets matrix. So you could rewrite it like this, but the process of convolution is actually a process where you can interchange alpha and beta. So you could also write it like this, which is sometimes slightly more efficient because you will have less floating point operations. So you could rewrite the process like that. So this is a way by which you now could encode the information and then simply perform this as a matrix times as a vector operation, which is something you can easily parallelize, you can easily run it on GPUs, etc. So this is very efficient to implement. If you see the operations here, you will see now that when you multiply here, you have beta 0 times alpha 0. So the first component would be obviously delta 0. And then you see the first operation gives you simply this one. The next line, if you take that one and you look at these operations, you see that the next one has beta 1 times alpha 0, and then beta 0 times alpha 1. And then you have zeros. So delta 1 is then simply given by these two guys here. And you see that when you perform the matrix vector multiplication and then you keep going. So this is when you implement the above operations, you normally do not encode or allocate memory for the matrices explicitly. You rather code the convolutions in the minimal memory footprint that they may require. So these matrices are often called tuples matrices, and that's a matrix in which each descending diagonal from left to right is a constant. So this matrix here is a typical example of a so-called tuples matrix. When you're dealing with there are some subtleties which we unfortunately don't have time to cover. And there's a lot of research which is going on concerning CNNs and Fourier series. So I just put up these links. So if you're interested in these topics, I invite you to take a look here. So when it comes to CNNs, if you look at some of these articles here, there is a lot of explorations on the type of filters you do. So if this is something which relates to your research, feel free to take a look at it. This is also something, if you want to study that as part of for the project, I think this is a very interesting avenue, but we won't have time to discuss that in the lectures here. So I just list this as a. Now, the thing which I want to do now is actually to generalize this expression here. So we said now that this expression which you see here is actually given or it represents just an instance of the process of convolution. And what I'm going to do now is to change a little bit here. So I'm going to define the filter, which previously was the lowest polynomial, which had only 3 components. And then X is the one which has the 4 components. So you could now think of us just taking that example, and I just want to rewrite it like that. So in our case, we had the 3 elements in the filter. And the problem is that when you now look at these elements here, when I've set up this automatically, what you will see now is that I may actually need a variable of X for -1 and -2, and they are not defined. So if I go back to the vector which I had here, let's just go up a little bit. You see now that I have 4 components for beta, which are now translated into X, and my alpha is being translated into W, the weight. So the weights have only 3 components, and the X has 4 components, and it's the X I want to scale down later. So what we end up with then is if we now just code blindly without thinking, you will see that this loop here will now give us elements of X. If X is I is equal to 0, then I'm going to start with something I could actually end up with, since this is free, I would actually get an element which is -2 and -1 here. So if I define in a brute force way an array which contains x0, x1, x2, and x3, I will run into one of the standard problems when you run a code, that is that you are trying to access elements which haven't been defined. And that's, you get a typical flyby, which says that you're out of the allocation of that specific array. And that's a memory problem. And your code just stops. So the reason why I bring up this example here is that this is a way to bring in the concept of padding. So what I'm simply going to do now is just extend the vectors by adding 2 numbers to the left and 2 numbers to the right. So I'm making it larger. It will have zeros, but I only include those elements which will allow me to perform the operation which you see here. So that means that if I now simply add some elements which are 0, and I do that by simply doing padding here. So I'm adding to that vector, which you see here, this X. I need now, since I'm running this in a brute force way, you will see that this will actually require that I'm going to access elements where I have -1, -2, but I will also get 4 and 5 here. So what I do then, I add 2 elements to the left and 2 elements to the right, and I augment the length of X from n equal to 4 to n plus 2p, which is 8. And 4 of those will be 0. So that is my padding. So it's a way to motivate why padding becomes important, because it then allows us to keep all the information which I want to have. So with p equal 2, I can now redefine. So I will have x0. I just redefine everything. So I have a new vector, and I have an x2, which is then equal to beta 0, x3 beta 1, x4 beta 2, x5 this one, and then I have x6 0 and x7 equal to 0. And then I simply rewrite my equation here. And then you can see that as an example, you will get some which are 0. This one will be 0. This is non-zero. This is non-zero. And then you simply have the expression which we had before. And if you do that for the 5th order term, you will see that x7 is 0, x6 is 0, and then you're simply left with beta 3 alpha 2. So then you actually, by just enlarging one of the vectors, you can then perform these operations in a straightforward way. And this is in a way what you want to do when you're dealing with CNNs, because you want to express in a compact way the transformation or the filtering by multiplying the filter with the input matrix. So yeah, these are just examples. So I've just been flipping the filter weight vector with the following terms. So I introduce a W2 here so that I can actually write this in a very efficient way. So instead of having W0, I have W tilde. And that way you see now I can simply write this as an inner product. That makes it very efficient. So you can then rewrite your bow sum as a dot product of these 2 vectors here. And at the end, this is what you want to do. You want to have an efficient representation of your input and your filters, and you want to perform this operation, the filtering, in a very efficient way. So if you the padding you have introduced for the convolution is just another hyperparameter which is introduced as part of the architecture, and similarly with the stride here. So if you look at one dimension, this is roughly what you end up doing. This is a convolution stage, but obviously you will not let this run from minus infinity to plus infinity. You would have this one rewritten in a way like the one which you see here. And you would encode this in these multiplications of 2 vectors as an inner product, which is something you can encode very efficiently on the computer. Do you see it? Is it okay? So when we now are going to scrolling down a little bit here, when you deal with 2-dimensional objects, which could be an image without the color channels, then what we end up doing is something like this. You can also, since it's a commutative process, which you saw from the beginning when we looked at this multiplication of polynomials, it doesn't matter when I do polynomial x times polynomial w or polynomial w times x, I should get the same result. So typically what you end up with is an operation which looks like this, where you obviously want to define these operations so that you have as little waste of CPU cycles as possible. So I just wanted to look at, if you now look at the CNNs in a little bit more detail, here's a simple example. And this is more relevant. This is back to the example which we started with in the previous lecture. So suppose this is your input. So you have a 3x3 matrix and you have a 2x2 filter. The example which I showed you earlier was just a simple polynomial multiplication. This is actually closer to what you end up doing in practice when you're dealing with convolutional neural networks. So if you look at that one, if you can introduce a hyperparameter stride, and then let's just scroll down a little bit here. So if you look at the final result, when you now have performed convolution of this process here, this is what you get. And this is what we actually put up before the break. So this is the final matrix, which is a 2x2 matrix, and it contains these results. And in this case, we have zero padding, so which means that x00 doesn't appears only in one of the elements here. But you can rewrite this, and this is the way you encode it in a more efficient way. So it means that you can rewrite this in terms of a matrix vector multiplication, which can be highly parallelized or also efficiently programmed on GPUs. So you could define, for example, that your input is now a flattened vector of length 9, and then you have a matrix W which has dimension 4 times 9. So that matrix could look like this. And that means that you can perform then the matrix vector multiplication of W times X prime. That is the same as this convolution which you have up here. You can easily convince yourself that that gives you exactly the same result with stride equal to 1. So it means that the convolution process you have here is something you can rephrase in terms of this vector here, where you have flattened out the input. And then you have rewritten this matrix here in terms of a 4 times 9 matrix. And when you do the multiplication, then that gives you as an output a 2x2 output matrix. You can easily convince yourself that that is the case. So the convolution stage then is a case where you apply different filters in order to reduce the dimensionality of an image. And that adds, in addition to the weights and biases, which are training by backpropagation, you have two new hyperparameters, which is called padding and stride. So here I just give a list of the same parameters which we discussed before we ended the previous lecture. So you will find the same information here. If you now look at the, I'm just going to skip this one because we mentioned that before the break. And so here's a typical examples, and these are also things which we went through before the break. So you will find the same information which I went through on the whiteboard. A typical example of what you end up doing if you have this kind of filters is that you extract a small region of your original image, and then you can scale it down. You have a kernel of 3x3, and then you end up with an output here, which could be an 8x8, depending on what your matrix looks like, or your input data look like. The other parameters I wanted to discuss a little bit is the so-called pooling. So pooling operations make up another important building block in CNNs. And they reduce the size of a feature map by using some functions to summarize subregions. So the basic, one of the standard pooling is actually called max pooling. So this is a way to reduce the dimensionality. So this image actually tells you a little bit about how pooling functions. So think now that you have an image which has these different values, and each one is subdivided in small blocks. So you can actually define how big these blocks are. So that becomes a hyperparameter. And then you can choose between max pooling and mean pooling. So max pooling means that your original one, which is a 6x6 matrix and has 36 entries, is now scaled down to a 2x2 matrix. And you see now that it takes the largest value and it carries only that one through the pooling stage. And then you do the same with the other ones. So 5, this is the max pooling case. And another alternative is just to take the mean value of all the variables here and then proceed with that. And pooling is the final stage of a convolutional stage. So you have the convolution itself with the filters. You have a ReLO output where you output the max of either 0 or the value. And then you have a final stage here where you now reduce the dimensionality further. So these are the stages in a standard convolutional neural network. And when we want to build our own codes, pooling, stride, padding, and the size of the filters, they become hyperparameters. which we need to define in the setup of a convolutional neural network. So if you want to build a neural network itself, what you need to do, and in this case, we are looking at the MNIST data set. And in this specific case, I just wanted to end the lecture here by showing you how you can define using TensorFlow. And we are coming back to this next week, because then we are going to discuss the codes in more detail and add some mathematics. There's a lot of deeper mathematics you can do about convolution, but we are going to leave that out here. But essentially, if you use Keras, you see now that you can define a convolutional layer. You define the number of filters. You have the size of the filters. You define the number of the max pooling. In this case, we have max pooling. And this is the pool size, which you want to reduce it to a 2 by 2. And then you flatten it out. And then you have a dense layer where you now have a standard rail as an activation function, a feed-forward neural network. You have a regularization part, which you can add. These are additional hyperparameters. And then you have the final one. This is the output layer, where you now define the activation function for the output. And if you have multi-class variables, like the MNIST data with 10 numbers, then you would typically use the softmax function. So we are going to look back at this next week. I'm going to skip the training here, but I also wanted to show you how you can run this with PyTorch. So in this case, there's an example with PyTorch where you have 2 convolutional layers, use max pooling. You have a dropout for regularization, which we haven't discussed yet, which we will discuss in more detail. And then I have 2 fully connected layers in my feed-forward neural network. And you can see now that the way you would set it up after you read in the data is actually in PyTorch and also TensorFlow with Keras. It's very easy to construct your own convolutional neural network. And we normally recommend, unless you want to write your own code, which we will discuss next week, then I would typically recommend using either PyTorch or TensorFlow. And you can see here, you define the convolution stage here. You have this is the size of it. This becomes the size of the filter. You have a new convolutional stage. You have a max pooling where you do a 2 by 2. You define the dimension of the final one because you want 64. So I'm making 32 replicas of the image. I have a 3 by 3 filter. I make 64 replicas. I have a 3 by 3 filter. This is the input. This is what I want out. I'm feeding in 64 times 7 times 7, which is a scaled down dimension. And this is the size defines the size of my feed-forward neural network, the hidden layer. And then I have a new hidden layer with 1,024 parameters, which then feed out to the output layer. So we will be discussing these in more detail next week. So I think I wrote in the email that we won't have time to cover everything. And next week, we are going to look more at the codes, but we will also repeat some of the basic mathematics next week. So this was a kind of top-down view on the way convolution is implemented. So convolution is implemented in terms of matrix vector multiplications. And in the code, which follows after the code in PyTorch or TensorFlow, there is an example of how you can write your own code. And this is what I want to discuss next week, because that's going to link with the mathematical operations which we have defined today. How you add padding, how you write that, how you encode the filters itself, and how you do the final training with the convolutional, with the feed-forward step. So after the break, we can discuss the projects. And I just wanted quickly to show you some of those which we are proposing. And then I guess if somebody wants to present what they have, we can also do that. We can do that first. But now we take a break of 15 minutes roughly.